When a retrieval-augmented generation system fails to answer a query accurately, the bottleneck is rarely the language model's reasoning capability. The failure usually traces back to a rigid sequence of operations during data ingestion. The traditional RAG ingestion paradigm relies on a strict order of events. Raw text is physically cut into isolated, fixed-size chunks before those chunks are passed to the embedding model to be converted into mathematical vectors. Consider a standard document where a city like Berlin is mentioned in the first paragraph, and a later paragraph references its population. If a hard boundary falls between those paragraphs, the text is split into two distinct chunks. The embedding model then processes these blocks in total isolation, analyzing the second chunk with zero awareness of the first. The pronoun reference is now immediately lost. This creates a document-level retrieval mismatch, where the true, continuous meaning of the text is stripped away, leaving only fragmented surface-level keywords. Because these foundational vectors lack global context, downstream prompt engineering cannot retrieve the correct antecedent. If the database cannot connect its to Berlin, the generation model will inevitably hallucinate an answer. To understand why this happens, we have to look past the macro document structure and examine the micro token level inside the transformer model itself. A standard transformer model does not inherently understand English. It builds semantic meaning entirely through a mathematical mechanism called self-attention. In self-attention, a token scans surrounding tokens, weighing their relevance to adjust its own meaning. But when the input is pre-chunked, that attention window hits a hard wall, mathematically blocked from weighing tokens on the other side of the cut. If a subject is trapped in chunk A and its referring pronoun sits in chunk B, the vector generated for the pronoun has absolute zero awareness of the subject. System engineers frequently try to mask this failure by tweaking overlap sizes or adjusting semantic boundaries, but that only treats the symptom of the fragmentation. Solving context fragmentation permanently requires abandoning pre-inference chunking altogether. We have to completely invert the pipeline's order of operations. This pipeline inversion is known formally as late chunking. The critical first step is to delay the cut. The entire raw document is fed into a long context transformer model as a single unbroken sequence. Modern models have the capacity for this scale. Jina's V3 embeddings, for example, can process context windows of up to 8,192 tokens simultaneously, roughly 10 pages of text in a single pass. During this forward pass, self-attention operates across the entire document. A token at the end draws a direct mathematical relationship back to the beginning. This bidirectional attention conditions every token-level embedding with the global context of the whole text. Unlike the traditional RAG pipeline, at this stage we possess a continuous array of contextually rich token vectors, but we haven't created any chunks yet. By processing the text before cutting it, we ensure the geometric space of every individual token contains the narrative DNA of a whole document. The co-reference blind spot is now fully eliminated. Once the forward pass is complete, the system transitions to the application of boundary constraints. Chunking logic is no longer applied to raw text strings. Instead, it is mapped directly onto the resulting array of token-level embeddings. Standard boundary strategies, whether fixed size, recursive, or semantic, are deployed here to determine where the cuts should occur across the token array. This leads to the final mathematical compression step, stand-specific mean pooling. The system isolates the token embeddings strictly within one specific bracketed span. During the pooling operation, all of the token embeddings within that boundary are averaged into a single output vector. This pooling process iterates across every mapped span throughout the entire document, compiling the data block by block. The final result is a series of standard chunk vectors, fully prepared to be ingested by any vector database. Late chunking decouples context generation from context storage. It allows developers to build highly granular search indexes without sacrificing the document's overarching narrative. Advancing retrieval precision usually raises an immediate engineering concern: exploding vector storage costs. This table compares storage demands of different retrieval architectures. Late interaction models store every raw token vector, causing massive database bloat, nearly 2.5 terabytes. Late chunking sidesteps this completely. Through final mean pooling, its storage footprint exactly matches the inexpensive, naive approach. Operationally, this means late chunking serves as a one-to-one drop-in replacement for traditional ingestion pipelines. The inversion happens entirely during the embedding phase, It requires zero modifications to the downstream vector database or the existing retrieval query logic. This architecture achieves high-end RAG scaling. It delivers the retrieval precision of complex multi-vector systems while maintaining the cheap storage profile of a baseline build. There is a misconception that late chunking makes traditional chunking algorithms obsolete. It doesn't. Instead, it acts as a foundational processing layer operating beneath your chosen boundary strategies. Higher-level logic stacks on top of this contextual foundation to determine the optimal mathematical cuts for specific document types. This layered approach significantly reduces the need for obsessive hyperparameter tuning, making the entire pipeline less brittle. During the generation phase, the benefits cascade. Returning fewer but highly precise chunks reduces the token bloat sent to the language model's context window. Leaner, highly accurate prompts directly reduce API inference costs and lower overall system latency. By respecting the order of operations and embedding text before we cut it, we elevate RAG from a fragile keyword matching engine into a structurally robust semantic reasoning system.